It didn't last very long.
I'm pretty sure half of it was gone by the time I left chemistry. So.
People are like, how many servings is this? And we're like, one. It's Girl Scout cookies.
Yeah, the tag-alongs, they give you 15 cookies.
Yes.
That's it.
Yeah. They're 33 cents a cookie.
It's terrible. If it's $5, you're paying 30 cents per cookie.
I can like smell this, just the almond.
No,
Okay.
but if they're $5 and there's 15 each, then it's...
Sorry, Patrick. They're distracted by Girl Scout cookies again.
Oh,
There's no tax on Girl Scout cookies.
Because you're not using anybody's.
When you buy them, they're just $5.
They're just $5.
I feel like a very underrated market is Girl Scout cookie resale. Like I feel like it's
Oh no, that's a real thing. You're just not supposed to do it.
But like I feel like
I was just about to say that.
like if I were to have a Girl Scout.
There's also an underground thing about Girl Scout cookies that have been discontinued.
That, I can
Oh
see
my
how that's like
gosh,
some
I remember
collector's
those
type stuff.
lemon.
Yeah, so the Savannah Smile, the lemon sandwich is like is the ABC baker, but like there was a Julianne Huber's mom had a case of Savannah Smiles, and she's like, I just want to donate these to your troop, and I was like, okay, and they were like a year old. And so then people would come to us and we're like, they're like, I want lemon cookies. We have these new cookies called Lemon Ups. And they're like, no, I want the old ones. And I was like, I have them, but they're a year old. And they're like, that's fine.
They're $50.
No, I just sold them for, because a case of Girl Scout cookies, 12 boxes, $60. So it was like she donated $60.
They didn't care if they were a year old. I mean, I guess they keep. They're kind of.
No.
Big.
Well, the lemon ups, the ones that
If you're getting the
bags.
Samoas, they'll keep
Hmm?
because they're
The
just
lemon ups,
plastic.
they come in.
They are in bags. And so
I
are the
know, wax.
s'mores. I prefer the cardboard boxes.
Yeah.
But they say they cost more to make and ship. So, like the other baker doesn't even have the cardboard boxes.
So how much
anymore.
do you like buy the Girl Scout cookies yourself, or do they give them to you to sell?
So our troop buys them from Girl Scouts, and then
How much? So and then you resell
and then
them.
we sell them, and we keep
So
the
how much
difference.
Do you get them for retail? How much do you get them for?
What do we pay for them? $4.60.
And then you sell them for what? 10
So you get 40 profit.
Yeah. So like if you go up to a Girl Scout troop, like if you're only buying Girl Scout cookies to support the troop, you're better off just giving them money.
Yeah.
Because like if you buy a box of cookies, it costs $5 to buy, right? And then the troop gets 40 cents. If you give them $5, they get $5. So
I feel like
yeah.
do you guys only sell cookies? Do you sell cookies throughout the entire year?
It's limited.
It's
I
like
feel like if you were to go and you were to buy up a lot and then sell them in the off season for like
That's-
$10 a box.
That's basically what I do. I generally will pick up a couple extra cases of like the really popular ones, Thin Mints, Do-Si-Dos, tags, and then like whatever else is left with the troop, and Samoas. Samoas sell really well. So I'll pick up some of those, and then people show up in like May, and they'll be like, I really wish I could get a box of Samoas. I'll be like, I got some.
From my trunk.
They're in my garage right now. But anyway.
You lose the value.
I
if you
literally
sell
bought a
them.
box just so like out of nowhere the other day because they were selling them at Carol, and we were watching film.
Who was selling them at Carol?
I don't know. It's like a interest. It
Uh-oh, turf wars.
Well, like there's an actual Carol troop for
No,
one.
it was like little kids.
Aww.
So like,
Oh,
I
man.
wanted
No, well, cause like Mrs. Graham's daughter is a Girl Scout. Like there's multiple ones. I'm just kind of like whose turf is Carol? Cause I want to honestly sell them at like at a sporting event.
That would be good.
But I don't know if Zableski would let me do it. But like if we could just prop up Girl Scout cookies and a little like.
Just like get a couple of kids and like.
I'm so sorry.
Go to spot 1.
Oh, I could just go park in my parking spot, pop the trunk, and just sit there. Be like, let's go. Who needs cookies? Anyway. Let's go. Yeah, yesterday. So there's a girl that lives across the street from me, and yesterday, so she calls Girl Scout cookies Josie cookies, and so yesterday she wanted to go sell cookies with my daughter, and so like this girl, she's crazy pants. Like she's got so much energy.
That's awesome.
So that's Josie and this other girl, and they go out. They sold 25 boxes of cookies in an hour.
Nice.
So But this, so Autumn is basically, she rings the doorbell and then yells, "Do you want cookies?" And Josie's like, "Would you like to buy some Girl Scout cookies?" And then people be like, "I like the peanut butter ones." And then she's like, "Do you like the sandwich cookies or the chocolate covered cookies?" She's very good. Like if they don't open with the name of an actual cookie, like she never uses the names of the cookies with them. So anyway.
Those wagons are stopped.
Yeah, it's because the neighbor is the cookie mom and I'm a troop leader, and so like I just have a lot of stock. Oh, the cookie moms. God bless them. Okay, you guys ready to talk about worksheet number 3? Yeah, of course we are. Okay. So here's how worksheet number 3 works. We are going to start using information from Unit 3 where we were studying kinematics. Do you guys remember kinematics? We were talking about the motion of objects. And we had our 3 master equations. And the thing that all of these guys have in common, let's see, these guys all have one thing in common with each other. Acceleration, 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 right? Right? And when we talked about this before, we made a little chart at one point where each of these equations has 4 variables in it. And so if we know 3 of the things, we can always solve for the 4th. And there's actually 5 variables there, right? Acceleration, initial velocity, final velocity, change in time, and displacement. So we've got 5 total variables. Every equation holds 4 of them. So if we know 3 of those 5 things, we can solve for the other 2. What we did in Unit 4 was study things about force. And so now we understand that force equals mass times acceleration. Look at that. There's acceleration again. So all of our equations have acceleration in them. And acceleration is the bridge between the two, right? We can talk about force with acceleration and mass, or we can talk about acceleration in terms of the motion of the object. So that's the tie between the two things. So now what we're going to start doing is bringing those together so that we can solve problems. Depending on what we know, we can use either force or motion mathematical models, where it says mathematical models, it means equations, to solve for acceleration, and then use acceleration to solve for whatever is not known. The way that most of these problems are set up, you're going to have to do at least 2 equations. Most of them are just 2. But you're going to need to do Newton's second law, force equals mass times acceleration, and then you're going to need to do something from the kinematics or the motion side. So just so we don't forget, if we see something that says use Newton's second law, it means that. Okay, any questions so far? We're going to do a couple of problems and try these out.
Wait, what are each of the equations? So the first, like the V of F.
They don't have names. Are you asking for names?
Yeah.
They don't have names.
Or like, what are you solving for each of these? Like,
It depends on what you don't know.
Okay.
So these are just describing relationships. It basically, remember, these come from us drawing graphs and then figuring out what the graphs look like, and then tying those to the variables that we were using. But these are the relationships that we're going to be focusing on. They don't have names. We just use them to solve problems.
Yeah, but like V of F, is that velocity final?
Yeah, so it's final velocity. So acceleration is A, initial velocity is VI, final velocity is VF. Change in time is delta T, and displacement is delta X. So remember that triangle means change. So that's going to be final time minus initial time, and final position minus initial position. And sometimes equations write those out. So if you see like a big page of kinematics equations, there's just a lot of different ways that you can write the same equations. But this, you can always boil it down to just those. Okay. So now we've got a race car and it's going to do a thing. Now, when I keep track of my variables for these problems, I keep track of my kinematics variables together and my force ones together. So here it starts with a race car has a mass of 710 kilograms. 710 kilograms is from the force side, right? Our force variables. So I'm going to make a list here for force variables. You might not need to write all of this out every time, but it's kind of nice to keep them sectioned this way because it helps with setting up how you're going to solve a problem. We put mass equals 710 kilograms. Motion variables. It starts from rest. So saying it starts from rest tells me something. It tells me that my initial velocity is equal to 0 meters per second. So make sure you don't miss that. Sometimes students miss that part where it says rest. So 0 meters per second, and then travels gives me a distance. Distance is a motion variable. Got a distance of 40 meters in 3 seconds. Now I already know 3 things on my motion list, guys. The car is uniformly accelerated during the entire time. How big is the net force acting on the car? So that's one thing I have to find out. Make a quantitative force diagram. Write a net force equation for the axis along which forces are not balanced. All right. So with this problem, we've got a car. It's on a road somewhere, right? So there's my road. I'm gonna draw my car. There's my car. For forces on my car, I've got gravity and normal force, right? But our problem doesn't really talk about those because our car isn't flying or lifting off the ground or anything. What we're worried about is how it's accelerating. And we know it's accelerating because it starts from rest and then starts moving. So it starts from 0 and then its velocity increases. So I don't know. I'm just going to call this the forward force. I'm not going to get stuck on what the name of it is. And then it's probably got something backwards too. So I don't know. I'm just going to call it friction. I know it's a little bit inconvenient that forward force and friction are all start with the same letter, but we'll just try to keep it straight. So here's our force diagram. If we want to make it quantitative, we can fill in some numbers here. We know that if our mass of our car is 710 kilograms, that gravity should be minus 7,100 newtons because we're going to multiply that by minus 10. Normal force should be equal to that, but opposite direction, so 7,100 newtons upward. It's hard for us to know what these two forces are, but we can say something about the net force, right? Because our net force is going to be equal to the sum of those two, the backwards force from friction and the forward force. Whoa. However, a G there, but sorry about that. And that the sum of those two things is going to be equal to mass times acceleration. So far, I've got my net force equation and I've got a quantitative force diagram. Now we need to figure out how big is the net force acting on the car? Well, to figure that out, we're going to need to do our net force equation equals mass times acceleration. Do we have enough information to do that? We have mass. Do we have acceleration? We don't. And so in order to be able to solve for this, we need to figure out what our acceleration is first. So to figure out our acceleration, find A or solve for A. What we're going to need to use is our motion variables to sort that out. We've got initial velocity, displacement, and time. We need to solve for acceleration. So we need to find an equation that has those 4 variables. If we look at the first one, we've got a final velocity, acceleration, time, and initial velocity. This doesn't incorporate distance, and it doesn't incorporate, and it has final velocity, which we don't know, so we can't use the first one. Yeah.
Couldn't we do just, since acceleration is distance over time squared, could we do 40 over 3 squared, which is 40 over 9?
We can check at the end and see if that works. So if what you're proposing is that, so does acceleration equal this? Right? Does that work? And so we'll double check that in just a second. So if we look at this next one, this next equation, change in x, we know that. Acceleration, that's what we're trying to find. Time, we have that. Initial velocity, we have that too. So if we have that equation, let's rearrange it and compare it to this. So we know that since our initial velocity is 0, that we can eliminate that, right? Because this. So that's going to equal 0. We don't need to include it. If we want to use this to solve for acceleration, what we need to do is multiply both sides by 2 and then divide by time squared. So the rearrangement of this tells us that acceleration is equal to 2 times the change in x over time squared. So why is that? Any ideas? It's just when we did the experiment where we were let's see, this came from the dropping balls in the online lab thing that we did. You guys remember? We're looking at displacement. So when you have an acceleration, it ends up this doesn't quite work out that way. Because we have to deal with this too. So just because there's a value there for that relationship, it doesn't work. It feels like it should work though, right? Because you're doing velocity divided by time. But you actually frequently will end up with the wrong value because of that. So it's close, and the units work, but just because the units work doesn't mean that the values are going to work. So just to figure out acceleration, then, so right now, put that there. Okay, so in order to calculate this acceleration, we're going to do 2 times our change in position, which is 40 meters, divided by our time squared, which is going to be 9 seconds squared. So this is going to end up being, I'm going to write 8.9, but it's really 8.888888, a bunch of 8s, and then a 9. And so in my calculator, I would actually just leave it in there as it was when I did the problem, right? So do 80 divided by 9. And then use that when I do my next calculation, because I don't like to round until I have to, until I need to write it down. For my calculations, I try to keep the whole numbers in the calculator. So then for the next step, I'm going to go back to the purple one, because that's what I needed to find is my net force. It's going to be mass times acceleration. The mass of our car is 710 kilograms times our acceleration, our 8.9 meters per second squared, and we end up with a total force of 6,311 newtons.
So we don't have to find what force forward is and what force friction.
No, just the difference between them, because you have to know more information to be able to do that.
How do you go from the first equation to the second one for acceleration?
This one to this one. I just wrote the word no.
No, the one above this.
This one
Yeah.
to this one.
Yeah.
So this one is just our regular equation from up here. I just copied it. And then I rearranged it. I had to multiply both sides by 2. So now I have 2x equals a times t squared. And I had to divide both sides by t squared. Like that. Does that make sense?
Mm-hmm.
I started messing around with this other equation down here to see if I could sort out how to connect those two. But I think if we kept expanding it, it would work.
What if you just put on 2x squared equal to t squared?
2x squared. Which one?
For that one. Well, I guess that only works when you have started 0, doesn't it?
Yeah, this only works when your initial velocity is 0. Otherwise, it's much more complicated. You can do it, except you would have this. But it would work. Do you guys have any other questions about that one? show you guys the second one, and then I'm going to have you guys just finish numbers 3 and 4. Numbers 3 and 4 have multiple parts, so it ends up being like 6 small things, but I think you guys can do it. Okay, so the next one says, suppose that a 1,000-kilogram car is traveling at 25 meters per second, 55 miles per hour. That's pretty familiar speed, right? Its brakes can apply a force of 5,000 newtons. What's the minimum distance required for the car to stop? So I'm going to just keep track of my information here. So for force stuff, I've got a mass of 1,000 kilograms. It says the brakes can apply a force of 5,000 newtons. So that's going to be our total force that's being applied, because you guys have driven cars, right? If you're driving a car and you're trying to stop your car, do you have any forward force? Do you do the brakes and the accelerator at the same time? No, that'd be a terrible idea. So I've got 5,000 newtons, and we'll do some more stuff in a second here. So it says, what's the minimum distance for the car to stop? So what we're trying to find is the total displacement. All right, what else do we know? We also know about our motion that our forward velocity is 25 meters per second at the beginning. So our initial velocity is 25 meters per second. What's our final velocity? 0, yeah, because we're trying to bring it to a stop. Okay, so down here in motion, we only have 2 things. If we have 2 pieces of information in motion, can we solve anything? No. How many do we need? 3. What do you think the missing one is? It's acceleration. So we're going to be able to figure out acceleration first and then use that to solve for a change in position. Do we have enough force information to figure out acceleration? We do. So we're asked here, what's the distance required for the car to stop? We need to make a force diagram, and we need to write a net force equation. So I'm going to draw my picture first. There's my road. Here's my car. Vroom, vroom. We've got gravity, which for our 1,000-kilogram car is going to be minus 10,000 newtons. We've got normal force upward, which is going to be positive 10,000 newtons. But that doesn't really tell us much about how our car is moving. Our forward force, do we have any forward force? No. Shouldn't have anything there. Because our car is trying to brake. So we're just going to have a backward force from the brakes. And what is the size of our braking force? 5,000. Should it be positive or negative? I like to make backwards negative. So I'm going to make this minus 5,000. I'm going to come over here and make it minus 5,000 on my list here. So to find our acceleration, we're going to take a look at our force information over here. And we know that Newton's second law says that force is equal to mass times acceleration. So solve for acceleration, we need to do force over mass. Our force is minus 5,000 newtons. Our mass is 1,000 kilograms. So we're looking at minus 5 meters per second squared for our acceleration, which means that as we're applying those brakes, the car's speed is being reduced by 5 meters each second. Now we've got 3 things in our motion box. So I'm going to flip the page and look for something that has initial velocity, final velocity, acceleration, and displacement. So here we go. There's final velocity, check. Acceleration, check. Time, don't have time. Displacement, good. We need that. We've got acceleration. Oh, there's time again. We don't have time. So down here we've got final velocity plus final velocity squared plus initial velocity squared plus 2 times acceleration times the change in x. That's the one we need. So I'm going to rewrite that on this side so that I don't get confused. I like to draw a line too when I'm doing like a first part and a second part, just so that I can kind of keep things straight a little bit. I'm going to rewrite my equation. Whoops, plus 2a delta x. And what I want to solve for is this guy, my change in x. So I also already know that my final velocity is going to be 0. So we're already at 0 equals initial velocity squared plus 2a delta x. If I subtract the minus vi from both sides, and then divide both sides by this minus 2a, I'm going to rewrite this a little bit so that my change in x is equal to minus...
Hello, Dr. O'Malley. Would you ask Logan Oblenis to stop by the office?
Sure, thank you.
Thank you. Bye.
Bye. All right, so our initial velocity is 25. This will be minus 25 meters per second squared divided by 2 times our acceleration, which was minus 5 meters per second squared. So this is going to end up being minus 625 meters squared per second squared divided by minus 10 meters per second squared. So our final displacement is going to be, look, this is going to end up being positive, right? That's what we would expect. If the car is moving in the positive direction, even though acceleration is in the negative direction, we're still going to travel a positive distance. The car's not going to travel backwards just because you're applying the brakes. Dang it. It's not 65, it's 62.5. So we end up with 62.5 meters as our final distance. What questions do you guys have?
How is the meter squared? Oh wait, never mind.
So it's meters squared, and then the bottom one is just meters.
Yeah. So the second squared completely cancel each other out. And then having a meter down here cancels out one of the meters in the numerator. All right, you guys ready to try some on your own? No. You're gonna do great.
I feel like if they told us what we needed to find, it would be a lot easier. Figuring out what we need to find. I just feel like
They do. They say find the minimum distance.
yeah,
It's either going to be that you're asked to find something in the force equation and you have to find acceleration for it first, or they want you to solve for something in the motion equation and you have to solve for acceleration first
Why
with the
did
force
acceleration
information.
go in force?
Why does what?
Why does the acceleration go in force and not the motion?
It goes in both. But we had to solve it using mass and force. And so that's why it showed up there first. Because all the green stuff was the stuff that we knew, and then all the stuff that I wrote, I guess it's kind of hard for you guys to see. So all the stuff that was in green was stuff that we were told in the problem, and then all the stuff in black was us solving it. You guys have any other questions?